And he's here to tell us today about the chemistry of the atmosphere. So please join me in welcoming Simon North.
All right. Well, thanks for coming, and hope you'll enjoy this a little bit. Thanks for embarrassing me, Eric. Yeah, no, I didn't have a standard route into chemistry. I was a music major and became a chemist late in life because of location. That's true. So what I'd like to do tonight is actually talk a little bit about atmospheric chemistry. And so this is an area that my research group has been involved in. And I think it's something that we should all know something about. And so the title is Chemistry and the Air We Breathe, a molecular view of the atmosphere, because I think atmospheric chemistry, and since you're all chemistry students, atmospheric chemistry is really about a molecular understanding of what's going on in the atmosphere. And so what I hope to do tonight is actually talk a little bit about what atmospheric chemistry is, why you should be interested in it, how far we've come, and talk a little bit about some of the problems that we've solved, some of the problems that remain, and the challenges that remain for people like yourselves to solve, if you so choose. Because it's my prerogative as a speaker, I'll also show you a little bit about what we do in our group and how it fits into the sorts of questions that I'm going to talk about here tonight. And so I hope you'll bear with me in some of the science I'm about to talk about as well. Anyways, we'll see how it goes. I hope by showing you some of the science that we do and the science that I'm going to talk about, actually some of it's in press and hasn't come out yet. Some of it is unpublished, so it'll give you a sense of really where we are today as opposed to, what I did, well, I'm not that old, a while ago. Okay, and so the thing that you should be thinking about as whatever you want to be is, what are the important issues for us to address in the future as people? And as chemists, we'd like to know what are the important issues for chemistry to address in the future. And there are all sorts of things that are interesting in chemistry, from materials to biomedical applications. But one of the things that we should all be aware of is that it's a very small planet. This is a picture of the Earth at night, totally at night. So this is taken by many images altogether that sort of shows the lights on the globe. And the population reaching about 7 billion pretty soon, one of the key issues is going to be our environment and sustainability and how we live in the world that we've been given. And so these are, I think, important issues for chemistry, and this is in the area of environmental and atmospheric chemistry. Now, really, what I'd like to show you tonight is that there's real importance to understanding atmospheric chemistry. And I'm just going to read you this, so bear with me. I'm sorry if you can read faster than I am. But it's been known for a long time that we can have an effect on our local environment, on the air we breathe. And this is a long time ago. This is a Hebrew philosopher. And he made the following statement, which is quite true. Comparing the air of the cities to the air in the deserts and arid lands is like comparing waters that are befouled and turbid to waters fine and pure. In the city, because of the height of its buildings and narrowness of its streets and all that pours forth from its inhabitants and their superfluidities, the air becomes stagnant, turbid, thick, misty, and foggy. There's no choice in this matter, for we've grown up in cities and have become accustomed to them, which is true for the population that we currently have now. Most of them are moving towards the cities. You should select from cities, the cities one of open horizons. Endeavor to at least dwell on the outskirts of the city. And he also makes some statements about how the altered air can essentially affect our way of being. And I think this is true today. This could be someone making this statement in the present. What was thought of, though, back then, which has sort of changed, is that the way we used to think about the atmosphere really was as some gigantic fluid that's sort of inert. And that although the cities were sort of impure from our pollution, the winds would come and carry it away, and it would go away forever. And then the next day, we'd generate the pollution, and it would be carried away again. But what wasn't thought of is really the world in general. And it's only a really recent phenomenon. how human activity actually can affect the atmosphere on a grand scale. And so I'm going to show you some evidence of that. Now, what is the atmosphere that we live in? Well, it's mostly nitrogen and oxygen, as most of you know. And in fact, although some of you may not know it, the third most abundant species is argon, a noble gas. And then there's lots of other things in the atmosphere: carbon dioxide, neon, helium, etc., all the way down. Here's carbon monoxide, iodine. But what you'll notice here is that the atmosphere seems mostly inert. I mean, nitrogen and oxygen are fairly inert at normal temperatures, and argon, you've got noble gases, and that things that are somewhat reactive, maybe interesting, down here, are all there in very, very little abundance. Now, what's sort of interesting is how far we've gone in atmospheric chemistry. Really, only in the last 50 years have we actually been able to measure these species that are in such low concentrations and actually understand how they change the air that we breathe. These are so small that you may think, why should we care? And so the idea of tonight's talk is to sort of give you a sense of why it does matter, these things in such small abundance. And even though we've actually affected the air in the environment, and you can see that here from an evolution of trace gas mixing ratio. So this is how the amounts of various species here, ppm is parts per million, ppb is parts per billion, and of course these species here are in parts per trillion. Okay, so very, very small amounts. You can see how the atmosphere has changed from pre-industrial times all the way through to 1990. There's been steady increase. These which are manufactured, essentially that did not exist in pre-industrial times, have grown and built up. But still, these are all there in part per trillion, so very, very small amounts. Okay? And so one of the questions that you should ask yourself is, how can anthropogenic, sort of human activity, so these are human emissions, of chemicals, which are so small compared to the mass of the atmosphere, have such a profound effect upon it? All right? And so that's a sort of a very interesting question, where you have so little material making such a difference. Why should we care? And it turns out that there are a few reasons why we should care. One, small amounts of molecules can act as catalysts for change. And so you've all studied about catalysts, and this means that a small amount of material that's released can act catalytically, and it can speed chemical reactions much faster than would happen without it, and they can be reused because catalysts are always regenerated. So only a small amount can do a lot of work, and we'll see that when we talk about stratospheric ozone. Also, some compounds can be more efficient in bringing about change than major constituents. And so I'll just sort of talk a little bit about this at the end of the talk when people are talking about global climate change, and we always sort of identify carbon dioxide. It turns out that there are lots of other species that we're emitting that are actually thousands and tens of thousands of times more effective in terms of the greenhouse effect per molecule than CO2. And so small amounts can offset, okay, their relative in abundance by having a major effect. And the other thing to sort of note is that small emissions can actually make a big difference if they're allowed to build up over long periods of time. So if things have a very long atmospheric resonance time, as they're released, they essentially build up and build up and build up. And over a long period of time, before you know it, you have actually appreciable quantities of certain compounds. And so there are a number of reasons why such small emissions, even though it's such a large reservoir, we should really consider the atmosphere as something that we need to think very carefully about. I like this quote because this sort of summarizes, I think, what you should leave the talk thinking about. This is from a German astronaut who went up to the space lab. And when he was in orbit, he made the following statement. You can barely see the atmosphere that he's talking about here in the curve. For the first time in my life, I saw the horizon as a curved line. It was accentuated by a thin seam of dark blue light, our atmosphere. Obviously, this was not the ocean of air I had been told it was so many times in my life. I was terrified by its fragile appearance. And so I think we should all begin to think of it, the atmosphere, as being something that is fragile, that we can alter, and we need to sort of make good decisions about stewardship in the future. Now, okay, getting to atmospheric chemistry now. I see atmospheric chemistry in this, this is just an opinion, as being really made up of 3 areas, so atmospheric chemistry research. And the 3 areas are atmospheric modeling, so-called laboratory studies or laboratory research, and field studies. And all these work together, really, and the goal of atmospheric chemistry is to develop predictive models, a predictive understanding of our atmosphere. So we can understand how the input of molecules into the atmosphere will alter its function and its chemical composition, and we can make informed decisions about our emissions. Now, what are these? Atmospheric modeling is really, it comes from the sort of the meteorological community, and that is actually people who do computational simulations of the movement of air masses, okay? So pictures of the air masses, circulation zones. But now, with computational capabilities getting better and better and better, these models can be of a global scale, and they can not only include the movement of the air masses, but actually the chemistry within the air masses in real time, okay? And so there's been real advances in computational areas to get very accurate atmospheric models, and those are constantly improving. Our group is mainly, although we do some field studies, mainly a laboratory group. And so what do laboratory chemists do? Well, we study the atmosphere actually in the lab, in instruments, and I'll sort of show you a couple of examples of those. And there have been huge advances now in laboratory studies, so we can look at very, very unstable species, intermediates, with very fast time resolution, very high sensitivity. And I'll show you a little bit about sort of what modern atmospheric chemistry looks like in a lab. The goal of the laboratory studies is to identify the species that may be important to include in the atmospheric models, to provide data on the reaction rates, okay, actually in the atmosphere between various species, and to provide that information to the atmospheric model so it can be included in the computational modeling. The other is field studies, and field studies is actually the measurement of what's out there. So it's people going out and looking at the atmosphere, making measurements to see what is there and in what abundance. Okay? And it turns out that all these work in a sort of together, and they all work in a sort of an iterative process where people may identify some interesting chemistry, ask the modelers to put it into their model, look at what the outcome should be. They'll talk to people in the field to see if, in fact, the model is correct. And sometimes the atmospheric modeling community will have a problem modeling the actual atmosphere that field people have looked at, and they'll come up with some ideas for new chemistry that needs to be included, and they'll ask people in the laboratory to explore it. So all these work together, and they're very, very different areas, but they're all very, very important to solving what is a very complex problem. All right. Now, one of the interesting advances in field studies, and this is something that you can spend some time, if you've got nothing to do with your computer, doing is, you know, we're just talking tonight at dinner. This is the 50th anniversary of Sputnik. And so it's really only been 50 years since we've had artificial satellites in orbit. And now we've just come to rely on them so much, and they've become a real, a crucial tool in understanding our Earth. And a website that's sort of fun is the earthobservatory.nasa.gov, where you can sort of download real-time images and data from all the satellites that are currently circling the Earth. Here's one, the Aqua, which looks at water particles and surface temperature. It's the lead in what's called the A train of a series of satellites that are all moving more or less in single file across, separated only by a few minutes each, that circle the Earth about 14 times per day and map it out. And so you can get pictures like this. This is a summer in 2003 of the Earth's surface temperature, basically from space. And so we're really working at, this is just to show you the advances made in field studies. People still are making ground-based measurements, basically with lasers, to do remote sensing and other advanced techniques, sending up balloons, high-flying aircraft, but also we're getting more and more satellites in the air to give us information about the Earth, and then we need the atmospheric chemistry to sort of understand what we see so that we can make predictions. Okay? And this is sort of a nice picture. The red is very hot, all the way down to the purple and dark blue, which is cold, and you can see the persistent equatorial thunderstorms as sort of this cool region scattering off the top of the clouds in the equatorial region there. All right, so what I thought I'd do is talk about three broad areas of chemistry. The first is the Antarctic ozone hole, which most of you should know something about. And if not, well then, this may be the first time. But I'm sure most of you have heard about the Antarctic ozone hole. And I've titled this an atmospheric chemistry success story because I think this is an example where we've really identified a very clear impact of human emissions or human activity on the atmosphere. It was recognized, it was studied, it was understood, and then we actually moved very quickly to do something about it. And so I think it is sort of a paradigm of sort of atmospheric chemistry. Okay, so just a few basic things about the stratosphere and stratospheric ozone. Okay, so the stratosphere, as you know, is, or may not, is a region of the atmosphere that's about 15, give or take 15 kilometers to 50 kilometers above the Earth's surface. And it contains about greater than 90% of all the ozone. So later in the talk, we'll actually talk about ground-level ozone, which is harmful and is a problem in Houston. But right now, we're talking about the ozone in the ozone layer, which is a band within the stratosphere where most of the ozone is located. And this is actually beneficial because, as you know, the ozone layer actually filters out the short wavelength radiation from the sun, which is damaging to us. And so it's of real concern. And it was known for a long time, in fact, back in 1930 with Chapman, scientist Chapman, who postulated that there should be such a layer of ozone, floating up at about 45 kilometers above the Earth's surface, shielding us, and came up with a mechanism for that. And it wasn't really until decades later that people could actually measure it and found out that what was there was less than what Chapman had predicted. And Chapman's mechanism was remarkably simple, but at least got the fact that there should be a layer and it should be located in the stratosphere. What turned out was that there was much less ozone than Chapman had thought. And the reason there was much less ozone was a mystery for a long time. And the reason is, and this will become clear later on, that it's very, very hard for species, chemical species that are released from the ground to actually make it up to the stratosphere, because the time it takes to actually get up there is on the order of 10 years or more. And most species have a very, very short atmospheric lifetime, and if it's less than 10 years, then it ends up being rained out or washed out or depositing and not making up into the stratosphere. So the stratosphere actually is a very rarefied region of the atmosphere. There aren't that many things up there. And that was the source of the problem, is that you have to come up with some sort of mechanism which will explain why the ozone is depleted and you don't have much to work with. And it was worked out by a number of scientists that there were these catalytic processes that depleted ozone. And that is that if you have a catalyst, call it X, reacting with ozone, you have XO plus O2. This XO will then react with an oxygen, a free oxygen atom, to regenerate the X, so it's a catalyst, and produce O2. And the net of this, the net reaction here, is that you're taking O atom and ozone, O3, and converting it to two oxygen molecules. And this is the so-called odd oxygen, which is good because oxygen atoms will react with O2 to give you ozone, and you're converting it to O2. And this X was identified as a number of things: hydrogen, the hydroxyl radical, NO, and Cl, for example. And so this was known for, this chemistry was known for a long time, at least for several decades. Well, it turned out that the British Antarctic Survey Station at Haley Bay was making measurements of the atmosphere above it and looking at the ozone column. These are in Dobson units here, but suffice to say this is really a measure of the ozone column. That is the total amount of ozone looking straight up, okay, that is in the atmosphere. These were all taken in October, so this is the polar spring when the sun comes out. And they'd been making measurements since the 50s, and they saw these sort of fluctuations, but over a sort of a long period of time, they were measuring in this range of 300 Dobson units. And at about 1979 or 1980, they began to see this decrease in the amount of ozone over the Antarctic. And this was about the same time, 79, when the so-called TOMS, the Total Ozone Mapping Spectrometer, went up in a satellite to take spatial pictures, and these are pictures of the ozone, so-called ozone hole, over Antarctica. And blue and purple are low values, reds are high values, and you can see this purple spot sitting over Antarctica. All right. And so this was confirmation then of these measurements that were being made by looking straight up through the stratosphere. And this was seen about this time between 1980 and 1990. In fact, there was a seminal paper published in 1985 which sort of actually announced this large decrease to essentially values that were almost a half of what it had been before. So it's a very, very significant change. There are sort of interesting stories about this, sort of one legend, and of course, that the TOMS instrument did not observe this, the satellite, because the code actually threw out low values of the data. So it actually wasn't in there until they went back and re-looked at the original data. But both the ground-based and the satellite measurements were in agreement. So what was this due to? Well, it had to be due to something that had changed, and it had to be something that was able to get up into the stratosphere to bring about this change. And so I just sort of summarize here mixing times and transports, and you probably forget this when you leave, but I'll need to put it up for this time. It's sort of interesting. There are very, very different mixing times in the atmosphere. The so-called vertical mixing time within the troposphere is weeks. That's essentially if you let something off outside this building and you just sort of watch it sort of vertically mix and go out of the boundary layer and up. That would take weeks to get out of the boundary layer into the upper troposphere. Mixing within each hemisphere takes months. So this is now taking whatever you released out of this building and mixing it within the northern and southern hemispheres. That takes months. So if species that you release outside this building last for months, chances are you'll see them, whatever you release here, over in Asia. Okay? It will be mixed in that way. The mixing between the hemispheres is slower. That takes about a year, but things that live, chemicals that last longer than a year can actually find their way from one hemisphere to the other. And so the rule of thumb is that mixing between the stratosphere and the troposphere, because there's a temperature inversion, actually takes years, on the order of sort of 10 years' time in that. And this is because things need to move to the equator and then sort of when the hot air rises, be punched up into the stratosphere and then settle out into the poles. And so it takes a long time for things to make it up into the stratosphere. So this ozone hole that was seen had to be due to something new that was in the stratosphere, and it had to be due to something that actually had a very, very long atmospheric lifetime. And this was actually known. So-called CFCs, as you know, chlorofluorocarbons, had been developed since 1930 and through World War II as refrigerants and fire suppressants and all sorts of things. And they were very successful because they were so inert. This is CFC12 here, CF2Cl2. And it's so inert, in fact, that they have atmospheric lifetimes in the troposphere on the order of hundreds of years. And it was known, actually, James Lovelock, in 1970, had actually measured CFCs, off the coast of England, and determined, really, on that basis, that the amount of CFCs he was observing was equivalent to all the CFCs that had been released up to that point. And so everything that had been released essentially had been building up in the troposphere. And at about this time, let's say 10 years later, Sherry Rowland and Mario Molina actually began to wonder, well, what will happen to these CFCs if they have such a long lifetime? Eventually, they're going to be transported up to the stratosphere. And up in the stratosphere, the wavelengths of light are short enough, because you begin to get into the ozone hole, so the light isn't filtered, that you can actually break these bonds and form free chlorine. And this releases now, your catalytic ozone depleting species into the stratosphere. And well, since it's a catalyst and goes through this cycle hundreds of thousands of times, a small amount can make a huge difference. And so at about this time, they recognized this impact in the mid-'80s and acted very, very quickly. This was recognized as the problem, and this is Kofi Annan, who said perhaps the single most successful international agreement to date has been the Montreal Protocol. This essentially, this Montreal Protocol in 1987. So remember, 1985 was essentially the year that this paper was published in Nature about the ozone hole, its existence. Quickly, the information was sort of worked out in the atmospheric chemistry community, and the culprit was identified, and then very rapidly, international community agreed to phase out CFCs and halons. And these are the projections then of the phase out. Of course, the atmospheric lifetime of these is so long that even if you stop emitting them, they still get transported up into the stratosphere over tens of years. And so it continues to build, and there are a number of other amendments to this which will bring down eventually in 2060, the chlorine in the stratosphere, because eventually it comes back down. These will come down to subcritical levels around 2060. And in fact, soon after this, we're beginning to see this increased trend, okay, from this time of the Montreal Protocol all the way to the Copenhagen Amendment. The Antarctic ozone hole is beginning to recover. Okay? Assessments are that in 2002 predict that by about 2050, so you should probably see in your lifetime, I hope, the full recovery of the Antarctic ozone hole. So this is really a success story, and of course the 1995 Nobel Prize in Chemistry was awarded to Mario Molina, Sherry Rowland for their work on the CFCs, and Paul Crutzen, who did a lot of work with N2O and nitrogen cycles in the atmosphere. Okay. Now, that's not to say it's a solved problem, stratospheric ozone. The Antarctic is a very, very special area, okay, for a number of reasons. And I've put in here, what about the Arctic or mid-latitude? Mid-latitude means not at the poles, but in from the poles. There we also see a depletion in ozone. That is much harder to model, and that still is an area of ongoing chemical research. The mid-latitude, although the drop in ozone isn't as significant, people don't live in Antarctica. So, you know, unless they're in the Haley Bay station. And so this actually becomes a larger issue, even though the drop is smaller. And so what I'd like to do now is actually just show you something that we're doing in our lab to address some of these issues. And so this is work that will address, I think, some of the issues in atmospheric chemistry. Now, this is the chemistry I showed you before. Cl reacting with ozone to give ClO, ClO going back to Cl and going round and round. This is basically chewing up ozone. This is what I've showed you before. Of course, there's all sorts of other reactions that are taking place. It's not as simple. One of the interesting things that can happen, though, and that is very, very important, is that ClO, which is an intermediate in the destruction of ozone, can actually react with NO2 in the stratosphere to form chlorine nitrate. And chlorine nitrate is a reservoir species. What it does is it basically takes chlorine out of this catalytic cycle here and sequesters the chlorine and doesn't allow it to be used for ozone depletion. So it's a very important compound, and it basically is formed by NO2. One of these sort of interesting issues is what happens to this chlorine nitrate? How efficient a reservoir is it? And when it absorbs sunlight and eventually falls apart, does it fall apart to give chlorine or does it fall apart to give ClO? And it turns out that that actually is an important issue in understanding ozone depletion at certain altitudes. And so let me show you a sort of what I think is a new instrument to look at this. And so this is a molecular view of atmospheric photochemistry. So I'm a physical chemist by training. This is the kind of experiment that I'd like to do if I could do it. And that is, can I take a single molecule of chlorine nitrate, let's say, and I'm going to take it and I'm going to put it in a molecular beam. What that means is I can basically expand it out of a jet into a vacuum chamber so that all the chlorine nitrate is going at a single speed in a single direction. And then what I'm going to do is I'm going to come in here and I'm going to use one laser pulse from a short pulse laser to excite the individual chlorine nitrate. It will fall apart, and then I'll come in about 5 nanoseconds later with another short pulse from a different laser, and I'm going to ionize the bits that come out, and then I'm going to take a picture of it. And I'm going to try and understand basically how fast that happens, what chemical bonds break, what do we form, and how it changes with wavelength. And this is the instrument I'm going to use. So I'm going to make a molecular beam here, I'm going to do some photochemistry here, and then I'm going to use what looks like a mass spectrometer with an imaging detector and a camera to take pictures of it. And so how does this, see if the animation works. So this is how we image. This is a schematic of it. We start with a molecular beam, so all our beams are all our molecules are moving in one direction, and then we come in with a pulse of light, and we cross that beam so that only a few of the chlorine nitrate molecules absorb. And here I've shown AB. It absorbs a photon of light, so one photon of light at specific wavelength breaks the bond. Which bond? Well, we're going to find out. Then we come in about 5 nanoseconds later, we shine another laser through it, and we take one of the species and we rip an electron off and we make a positive ion. And once you form a positive ion, you can use electric fields then to direct those ions down until they collide with this is a microchannel plate to give off a shower of electrons that hit a phosphor screen, and we take a picture with a CCD camera and we end up with an image. Okay? So what is this? Every spot on this image represents a single A+ molecule hitting at a position on the detector, coming from a single molecule of chlorine nitrate absorbing a single photon of known wavelength of light. So this is as molecular a view as you can get. And the idea is we're going to try and interpret these images to get understanding about what happened in this first step. And you can sort of think immediately, well, it's really a clear picture. The more energy that was released, the farther out the spots will hit, the ions will hit. And so the radius of an image like this tells us how much energy was released, where the energy went. And why is this got all these ions hitting at the top or at the bottom and at the top? Why don't they hit everywhere? And the answer is because when we excite the molecules, we line them up, and if they fall apart before they can rotate, the molecules that come out going up and down. And so the fact that it's not a ring tells us something about how fast the process happened. And we can clock this down now to about 500 femtoseconds. All right, so what are the questions in something like chlorine nitrate? Well, the questions are, for example, what chemical bond do you break when it absorbs a photon? Do you break a CLO bond and form chlorine plus NO3? Do you break an ON bond and form CLO plus NO2? Or do you break an ON bond here and form an oxygen atom? And what people had seen before was this oxygen atom, and they didn't know where it was coming from. And what is very difficult to measure is the amount of each of these channels that you see. And so why do we care whether we form this or this? This is the reverse of the formation. So this is basically chlorine nitrate forming and going back apart. This releases chlorine, which is basically the start of the ozone depletion cycle, and NO3, which will absorb sunlight and give a small amount of NO, which is another ozone depletion species. And so this channel is very bad. This channel is less so, it's more benign. And the branching from that determines how much ozone depletion we get at various altitudes. What's also interesting is if we put enough energy in this system, can we make an NO3 that is so hot and so energetic that all by itself, just by putting in one photon, we actually get 3 products out? And if we do that, we should get an oxygen atom. Is this the oxygen atom we see or that? And to make a long story short, we've actually done these experiments. This is chlorine nitrate absorbing light in the ultraviolet, and these are taking images of the chlorine atom and the oxygen. Very different images. But from the analysis of these images, you have to take my word for it, we can actually determine that these are essentially formed in equal yields, 50-50, and that about 20% of all the NO3 we form actually falls apart to give oxygen atoms. And we get that from this image here. And that turns out to be a very important thing because this is something that people hadn't known, and it makes this channel more benign because essentially you're releasing odd oxygen that can form ozone and you're removing NO. And so this actually we can measure actually directly and come up with unambiguous evidence for. And so the question now is, now that we've measured this as a function of wavelength, this is unpublished, how does this affect ozone depletion in the mid-latitudes, right? So this is be up to atmospheric modelers to put this new chemistry in their model. All right. So on to a sort of a different topic now that's sort of closer to home, and that is tropospheric chemistry. The troposphere is the lowest part of the atmosphere. It's where 90% of the air mass is. And the question here is air quality, and really what I'm going to talk about, and when I talk about air quality, is really ozone, again, because it's sort of a common theme. And so we'll look at ozone. We've looked at ozone in the stratosphere as something that's very good, that we need to take care of. And now we're going to look at ozone actually on the ground as something that we need to worry about, because it's poisonous, although how many people like the smell of ozone? Have you? I do. Okay. Anyways, you smell ozone in thunderstorms because you get it from lightning. If you're in a Xerox room, it's that sort of fresh smell of, it's a poisonous gas, but I like the smell of it. It reminds me of thunderstorms in New Hampshire when I smell it. Our lasers in my lab generate lots of ozone as they go through the room because they break down air. I like the smell. My students hate it. All right. So I titled this An Atmospheric Chemistry Work in Progress because I think the stratosphere is a hard problem. The troposphere is a much harder problem. And we've made a lot of progress in atmospheric understanding the troposphere. But it's a soup. It's a mess. There's many more species. The stratosphere is relatively pure. Very few things actually make it up into the stratosphere. But everything that we make is moving around in the troposphere, and so it's incredibly complicated, and it's a difficult problem. But I'll show you some of the things that we're thinking about. So why do you care? There's Houston on an incredibly clear day, and Houston on a not-so-clear day. And this is photochemical smog. Okay? And what we're talking about here is tropospheric ozone. The natural background of ozone is roughly about 20 parts per billion, 25 parts per billion, in very remote areas. And this is fine. You can do nothing about it. A lot of it comes from basically tropospheric-stratospheric exchange, so downward motion from the stratosphere where ozone is produced in large amounts. However, people often have observed ozone levels of greater than 120 parts per billion. It's still parts per billion, but it turns out that these levels are not good. And this is often observed near urban centers. To give you a sort of perspective, the EPA air quality standard, 8-hour standard, is 80 parts per billion. And so that sort of sets a limit to what EPA will tolerate in terms of air quality. And this data is kind of old, but you sort of get the picture. How many people from Houston? Yeah. So Houston, number one now. It used to be LA was number one. But in terms of air quality, I think Houston is the most interesting polluted place in the country. No, it's a fascinating place. For atmospheric chemists, we just had Texas Air Quality Study 2006, which brought people from all over the country and all over the world to study air in Houston because it's such a fascinating place to do research. And what I've showed here is the number of days exceeding the ozone standard. And there it is. So about 50 days out of the year, you've exceeded the standard. What is a bit disturbing is that in the early 80s, Los Angeles, the number of days it exceeded, how many do you think? 160 ballpark, sometimes 180. So almost half the year was exceeded the EPA standard. Since that time, LA has actually come down about 75% in terms of their noncompliance. So they're wavering about 40 days per year, noncompliance. Houston has come down a little bit, but is still about 40 and a little bit above. So in fact, LA has come down, and Texas is now, by default, the leader in days of noncompliance with the EPA ozone. So it's a big issue, and what to do about it, it's a difficult question. And so what atmospheric chemists are trying to do is understand the chemistry well enough for people to make informed policy decisions about what your speed limit should be or what your emission standards should be. Okay. All right, so just a little bit of, well, it's not a little bit, it's going to be a lot of chemistry. Here we go. So quickly, the role of NOx, NOx being NO and NO2. You've got destruction of ozone by NO. NO reacts with ozone to give NO2 and O2. That's pretty simple. You've also got NO2 absorbing sunlight to give oxygen atoms plus NO, and that oxygen atom reacting with an O2 to give ozone. And so what you can see right here is if you've got NOx in the atmosphere and nothing else, you have this equilibrium, this steady state. NO is being converted to NO2 and killing ozone. NO2 is absorbing sunlight and giving you back ozone. And this is in steady state. And so in a clean atmosphere, you've got NOx emissions from, in urban areas from fossil fuel combustion, but from soil, from lightning, from all sorts of things. And that gives you this NO and NO2. And then it goes around the cycle. Ozone's destroyed, ozone's produced, and the NOx is eventually removed. And so you've got this sort of nice stable system. The problem that you have in terms of urban air quality is that you release volatile organic compounds, carbon, hydrogen containing species. So these volatile organic compounds, VOCs, actually upset this balance. And I'll show you in a second that the hydrocarbons that you release react to form RO2. And these RO2s are what we call peroxy radicals. And these RO2 react very quickly with NO, and the NO pulls off one of the oxygens to give you RO, and you convert NO to NO2. And what this does is give you a net production of NO and a net production of ozone. And so you shift the equilibrium, and you end up with higher than background levels of ozone. And it's really the interaction between the hydrocarbons, which can come from a variety of places, as I'll show you, and the fossil and the NOx that's out there. And so you need both components to get this chemistry to work. And it's called, of course, photochemical smog because you need the sunlight to drive the destruction of NO2, right, to give you ozone. Okay, so this is about as simple as I can make it. This is what happens to, this is the fate of a hydrocarbon. Methane, ethane, propylene, butene, whatever you want. You throw it up in the atmosphere, and it reacts ultimately with OH. This is the hydroxyl radical. If you go outside and you take a milliliter of air, so 1 cubic centimeter of air, you actually will have about 10 to the 19 molecules in that cubic centimeter of air. 10 to the 19. During the day, you'll have about 10 to the 6 molecules of OH. So it is subpart per trillion, but it is responsible for essentially cleaning the atmosphere. It is the detergent of the atmosphere. And it's a detergent because it's a catalyst. And what happens is the hydrocarbon reacts with OH, and this takes anywhere from an hour to 10 years. So it's the rate-limiting step. And then once you form this radical, this step takes a microsecond, this step takes this step takes a microsecond, this step takes a millisecond, this step takes a nanosecond. So essentially what happens is as soon as OH finds your species and reacts with it, your hydrocarbon, the rest of the chemistry just happens very, very fast. And so this is the rate-determining step. But you can see that the OH reacts to give a radical, and then it's O2 reacting with this radical to give the peroxides. And this is the chemistry that I showed on the last slide. NO pulls off a hydrogen, you get NO to NO2 conversion, that gives you ozone. What can also happen is NO can actually just stick to the peroxy and make a nitrate. And why is that important? Because that is pretty stable, and it can be blown across to Mexico or wherever you want, and actually then release species that you don't want somewhere else. Well, if it's your species, it's fine. If it's someone else's species that's blowing in, it's unacceptable. Okay. And so what I'm going to do now is tell you a little story about sort of an area that affects regional air quality, and this is biogenics. And so this is actually an interesting case. I've told you that you need hydrocarbons. I've told you need NOx. You need both of them to get ground-level ozone. But I think what's interesting is that the hydrocarbons don't necessarily need to come from us. They can come from plants. And so we've been studying, actually, biogenic emissions, and what we've been focusing on is isoprene. And it turns out isoprene is a monomer of latex, but it's essentially emitted from from oaks and all sorts of broadleaf plants. And it's emitted at 500 teragrams per year globally, which is about as much as methane. The only difference is that it reacts in an hour and methane reacts in 10 years with OH, which means it is so much more reactive that it drives almost all ground level chemistry, ozone production in the US. Okay? Now, we call these non-methane organic compounds. The importance of these biogenics is that they basically they're emitted in huge quantities, much greater than man-made emissions, and that they essentially drive almost all ground level ozone, about 90% in the state of Texas, about 75% in parts of the US, and they do other things in terms of producing aerosols and things, other particles that we don't want. A statement that Ronald Reagan was derided for in 1980, his quote is, approximately 80% of our air pollution stems from hydrocarbons released by vegetation. And it's not that vegetation is the root of our pollution problems, but it in fact is a true statement that I would say 80% is pretty much correct. About 80% of our ground level ozone is produced from the oxidation of these biogenic hydrocarbons. Okay? But remember, you need two things. You need NOx and you need hydrocarbons. Okay? All right. And this is the people that raised their hand when they said they live in Houston. This is the interesting issue in the state of Texas. This is a model. This is Professor Rennie Zhang and co-workers in the Atmospheric Sciences department here. And this is a model that they were running on Houston air quality. And you can sort of see the ship channel there. This is sort of downtown Houston. And this is the emission of anthropogenic. These are man-made volatile organics. And you see it's sort of localized in Houston, lots of butene and things like that. This is the NOx emissions, huge amount, again, coming from Houston. And surrounded, okay, green is high quantities, surrounded by this vast amount of live oaks and everything else, which are giving up tons of isoprene. And so what we're really concerned about in a place like College Station is how this fossil fuel NOx and things that are released here are transported and begin to collide with biogenic hydrocarbons, which are on the outskirts of Houston, because this gives rise to these very large areas of high ozone in the state of Texas. Okay, now, I'll have to do this pretty quickly, but why do we want to study something like isoprene? Well, it affects all atmospheric chemistry in the state of Texas. It's very, very important. And in order to do true ozone forecasting, where we actually predict, like the weather, is it going to rain this weekend? We would like to be able to predict, is this weekend going to be high enough in ozone that you should probably just stay inside and watch the TV, or is it going to be a relatively clear day from an air quality standpoint? And the reason the chemistry is so hard is what I showed you before is just sort of schematic. You can see that isoprene is actually a complicated molecule, and OH, when it attacks isoprene in this first step, actually can add to 4 carbons, and it gives you 4 things, and then the O2 sees that and can give you more chemistry. And then all these things go on and react in complicated ways to give you a whole set of final chemicals that also affect air quality. It's complicated. And this is methyl vinyl ketone and methacrylene. If you're interested, that's what you're being exposed to. And so all this is very, very hard. And I'm just going to show you one little piece of the puzzle and then to give you an idea of what we do. Okay. This is the standard model of what goes on in the chemistry. This is what you'll find in your chemistry textbooks. Right? Well, not in your chemistry textbook, but if you pick up an atmospheric chemistry textbook, this is the model you'll find. And the question is there new chemistry that people haven't thought of? And when we looked at these, we began to think, well, this is really not the kind of chemistry that should happen to these. Because if we just look at this one component, okay, so just blur your eyes and just look at this one species where the OH adds to isoprene in one particular way, it turns out that organic chemists, like Eric Simonic over there, have known this for a long time. This is what that looks like, and that actually can form these rings and come back again very fast. And that's not in any of the atmospheric models. So what happens if this species here forms a ring very, very quickly? Well, this is the species we make. And what if it forms a ring? And then this bond doesn't break, but this bond breaks. Then we get something that looks different. And in fact, this is a beta hydroxy radical because the radical, this unpaired lone electron, is one carbon removed from the OH. Here it's an alpha because the electron is on that OH group. And it turns out that this is important because the standard chemistry says this will react with O2, but the alpha hydroxy radical, these things react differently. These don't form peroxies. These actually, this hydrogen is very weak, and the O2 just comes and rips it off and forms a stable molecule that's different. And so why do you care? Well, it turns out that every molecule of OH that encounters an isoprene is catalytically regenerated. And in the process of going around this loop, it converts two NOs to NO2, two of them, which ultimately gives you 2 molecules of ozone. And then you regenerate the OH. In the new chemistry, this radical just quickly forms a stable molecule in HO2, which gives OH just by one step. And so you actually reduce the amount of ozone that's produced in this chemistry. And so you should see very prompt regeneration of OH, no peroxy radicals. And so the question is, as scientists, is this occurring and should this have a big effect? And so the first thing is it occurring? And what we needed to do was actually make this species. And what we used is we had to synthesize something which we can shine light on to make it. And this is something that actually is very interesting. If you form a chemical bond, then you release a lot of exothermicity. It's an exothermic reaction, so you release all that bond energy into the molecule, and it's very hot initially. And so in the atmosphere, these molecules are born at thousands of degrees relative temperature. And so what we want to do is we need to shine the light on it, make this thing, but we also need to make it thousands of degrees hot. And so we actually can do this. So my graduate student synthesized this species here and put an OH and an iodine across this double bond. We shine light on, we break that iodine off, we get this and an iodine atom with a laser. So we can make this species. And now we just have to tune the laser so that we can make this hot enough. And the question is, how can we check that the energy of these radicals? And the answer is this ion imaging that I talked about before. And this is an image of the iodine coming from that precursor. So what does the iodine tell us about the radical that we're trying to make? And the answer is that we put in a photon of known energy. We know what color light we're using. We know how hard it is to break the bond. And whatever's left over is the energy available to the iodine and the radical. And that energy can go in only 2 places. It can go into the internal energy, the heat of the radical that we make, and the speed at which the iodine and the radical separate. And we know that because we know the bond energy, we know what photon we're using. We measure that from the radius. And so by difference, we get the internal energy. So we can actually measure the internal energy of this radical that we made precisely. And we can tune the laser wavelength to tune the energy of the photon until we get the right energy for it. Okay? And so, the question is, can we actually observe this? And we use a different kind of experiment where we're going to now put the precursor in here. In the presence of O2 and NO, we're going to put the precursor in. We're going to shine light on it to make the radical. And we're going to use one laser to do that. And we're going to come in a little time later with another laser. And we're going to look at the OH to see if we make it, and we make it quickly. And so we're going to use this second laser to light up the OH and detect the fluorescence coming from the OH molecules. And the end of the story is what we should expect in the traditional model, the old model of chemistry, is that it takes a very long time to regenerate OH. And in fact, the prediction there is that we regenerate OH way off the screen. In fact, if we go very short around the cycle and we see this new chemistry, we should form the OH almost instantaneously and see a very short rise. And this is in microseconds. And in fact, the data here is the fluorescence of the OH, here at different concentrations of NO and O2, and the lines are the expected prediction for this new chemistry. And so we can actually show that. Now the question is, again, this is new results. Will this impact, basically, our models for biogenic oxidation in the state of Texas. How will this affect ozone forecasting? And so I have to wait to see that. Now, in the last 2 minutes, because this is not an area in which I'm an expert, but I would just want to mention that there's been a lot of talk about global climate change, and I would say that for the next generation of scientists coming out, this will be, I think, one of the central challenges. And so while we know a lot about global warming potentials, that is how the species that are released into the atmosphere affect on a per molecule basis, basically how each on a per molecule basis, how these things, affect radiative forcing, that is what their effect towards global warming is. We also have long records of how these species are changing, and so these are the global CO2 concentrations. This is the steady rise in CO2. This is well understood. This has been mapped out here at Mauna Loa. You can see the oscillations from the different seasonal variations. And you can go back, it's very interesting, in time, all the way back to millions of years before present, and you can actually see that this rise is actually a very, very steep part of this curve. And this is the concern that a lot of people have. The other thing to notice is even if we go back, say, millions of years before present, if you look at the CO2 concentration, it is always about 300 or less part per million. And in fact, we are just about up to 400 parts per million. So we're in fact going into in an area where we haven't been in millions of years. And so this is sort of a concern that some people have. What is the increase in CO2 due to? Well, this is a fantastic stoichiometry problem, freshman chemistry problem. You can actually look at the CO2 levels, calculate how much atmosphere there is, what the average molar mass of the atmosphere is. This is dimensional analysis. Okay? There's about 1.8 times 10 to the 20 moles of gas in the atmosphere. The mass of carbon from fossil fuel is about 6 by 10 to the 12 kilograms per year, or 5 by 10 to the 14 moles. And that's an increase of 5 by 10 to the 14 over 1.8 by 10 to the 20. It's about 2.8 part per million per year. What we're seeing is about 1.5, 1.6 part per million increase. This doesn't take into account the loss of CO2 into sinks like the ocean, and so this pretty much explains where this recent rise is coming from. This is all fairly well understood. This is where there's future work for chemists like you. The greenhouse gases contribution to global warming and radiative forcing is well known. Level of scientific understanding high, but there is a lot to be learned about the impact of other things, such as aerosols and the aerosol indirect effect. And this is going to be the sort of the modern area that I think a lot of atmospheric chemistry will move into. So, hopefully in the talk I've shown you that atmospheric chemistry actually is a rich, rewarding area of study that I think has made huge strides since 50 years ago when we really thought the atmosphere was fairly inert and we didn't have measurements of almost any of the trace gas species, to one which is solving real problems in real time. Atmospheric chemistry has impacted the way we view our environment and the way we live, and I think that's been demonstrated. And I think what I want to leave you with is that there remain unanswered questions, and actually unasked questions, in the field of atmospheric chemistry, waiting for people like you, if you're interested in environmental chemistry, to solve. So with that, I'll take any questions that you may have, and thank you very much for having me here.